Moniz will tell us about the quantum cosmology and non-boundaries.
I don't know. I hope so. Oh yeah. I already feel a different pull of gravity on my neck, but so this is the talk. What is that? Right. Okay. So to begin with, I would like to be thankful to the organizers, and namely to Savan, which is not here, but for inviting me. I also hope that the slides that I've prepared, I only took about 2 months because I was incredibly busy, really, and that they will meet your expectation. Moreover, and I would like also to say that the title might sound a little bit iconoclastic in the sense that I will going to throw away every boundary. It's not the case. It's actually, it's actually a question. And a lot of questions remain regarding quantum cosmology, even if the subject has been improving and emerging and being built since, say, the late 50s. It's actually true. So in this sense, I will cover some of the basics. So nothing that you will be seeing here is actually original from me. It's from all other founding fathers and old masters. So I will hope that the ideas and the concepts I will bring here are clear for you. Then I also suggest that you feel free to ask any questions at any time, namely during the week. I don't promise to be able to answer all your questions, but I will surely be able to meet and contribute to your questions because there are still a lot of open issues that remain, so that in spite of all the brilliant work that has been done. So I will summarize what has been known, what we think we know, but actually we don't know. So there is also quite a lot to be done. And I was told by Sravan that there will be a lot of PhD students, young minds here. So I hope that this will also be positive motivation for them to work on. I would also like to make a disclaimer, and the disclaimer is the following. I've been involved through the past academic year under very strenuous academic management. Some of us that here know about it, and this has been a bit of a mental exhaustion. So don't worry, I will not do anything indecent in front of you, but I might be a little bit slow. So that's just the point. I'm trying to be gentle, and I will be doing the best of my ability. Let's see if I can continue. So let's make also a presentation, which, as I said, I'm going back to the 1950s, to the ADM formulation and all of that. And I also like to now do a little bit of another disclaimer. I'm being conservative. So I'm taking a metric representation. I'm leaving and putting all what is the loop quantum gravity and connection and architecture to Francesca. She will be doing the avant-garde and the new stuff. So I'll be doing metric. And this is something that is fairly well known by all of you, I think. So I'm just taking forcefully split. We need to do something to start with. If it works or not, it's something that only the results and the falsibility can help. And I'm taking a slicing of the universe in the sense like in an onion with hypersurfaces, which I label with a parameter, which I put it t like in time, and I put some coordinatization. And this is something that is fairly well known and on, say, I think it's chapter 20 or 21 in Misner, Thorne, and Wheeler. And all the calculations are basically done there, like in also other brilliant books by Ryan and Shapley, and also by Mike Ryan regarding Hamiltonian cosmology. All is there, or also maybe in the book by Klaus Kiefer. So basically, we are doing some slicing in hypersurfaces, putting some coordinatization, lines of constant values of these coordinates, and I'm taking the possibility that I can change the parameterization on the hypersurfaces, and instead of moving along lines of constant x, I could go along the normals, and I have to introduce something which then I need to do to present for my space-time metric. So this is something that is well known. So as I said, I'm just doing what I hope the organizers through Sravan told me, be pedagogical. So I'm really, perhaps, if I'm overdoing it, you just wave and I'll try to speed it up. So, it's fine. Thank you. Yeah, you're very kind. You're very kind. Thank you so much. So, so in the end of the day, we can write the metric in this convenient way. So this is already a choice. You are not obliged to do so. I'm already putting this convenient way where you have something that we call the shift vector and the lapse function, which is just names that you put in your assistant language, how you split and slice your space-time. So this actually the Adler, Anovitz, Dessner, and Misner parameterization, which allows to open up the road for Hamiltonian gravity. But then the point is that you can actually write new terms, which will be extremely useful. You will see why. You can say either compute the tree curvature in terms of the free metric, or you have the extrinsic curvature, which has to do how you embed the hypersurfaces in your space-time, and you calculate them or you define them using this mathematical symbol as the covariant derivative of the normal using the 4 metric, or you can rewrite everything in terms of covariant derivatives of the free metric. So this is just something that as you pass the pages of Misner, Thorne, and Wheeler, everything is actually brilliantly presented there. You get this. So the point then is, as I said, I'm doing the conservative bit. I'm taking Einstein-Hilbert, no string, so it's really the plain stuff. So the only new stuff that I'm putting here, which is not forcibly for some aspects, is this boundary term, which is important when you try to have the Hamiltonian equations of gravity to cancel the fact that in the 4-dimensional curvature, you have second derivative. So you need to do this when you are in some way to have a well-behaved Cauchy problem. So I'm actually, let me just say this also as a bit of disclaimer. So this is a huge field. So just the conservative, it's one term, so almost one semester course. So I remember this as a Michaelmas. So and it was really narrow. So a lot of things. So I'm presenting here in a flash short items. So a lot of things will remain to be addressed. So I invite you, if you are willing to learn from it, to go to some of the bibliography that I will put in there. So in the end, it's just you pick up your Einstein-Hilbert. Let's assume you use still this boundary term. This is actually called the Gibbons-Hawking-York boundary term for a reason that is really useful when you try to use this to compute Euclidean quantum gravity for black holes, and you want to get rid of those boundaries to compute probability amplitude. This is just a bit of a jargon, but that's why it is there. But then you put that metric inside of your Einstein-Hilbert action, and you get this. This is just some matter. Doesn't matter. It's not important. But then that's the beauty of the ADM. You got able So those people, Arnold, Dessner, and Misner, were really clever. So they did a brilliant thing. Though they pick up the action or the Lagrangian, they write it in a way that then you can extract canonical momentum, some which we call like primary constraints, then the canonical momentum of the trimetric, or say of the scalar field, and then you rewrite. You can rewrite the action in this way. So this is just label. This is just, but you can see here how important is the lapse and the shift, lapse function, the shift factor. When you go to assuming by hypothesis that you are having a homogeneous and isotropic, so you have to select it as your starting principle. You take this as your sort of a gospel. It simplifies, and this can be thrown away. When you have an isotropy, sometimes you cannot go away of it. And then there are also idiosyncrasies. Either you have Bianchi class A or you cannot go to Bianchi class B. It's not simple. So things are simpler when you take simpler hypotheses. Beyond that, there is a lot of work still to be done. So maybe then this will help to cement my words, which are just conveying the brilliant work by ADM, and also then by others like Wheeler and Bryce DeWitt. So this is also late 1960s. This is brilliant. There are 3 works by Bryce DeWitt, which are just mind-blowing. So you try to study and go through them. How could this think of this? So in the end, you can rewrite an Hamiltonian, which the important pieces are this, say, the orthogonal, say, in the direct computed through the normals to the upper surfaces, which is something that we can almost associate to an Hamiltonian with a kinetic term, with something that is called the DeWitt metric, with a new tool that he conveyed as superspace, which is not the same superspace, although the words are the same, like in supergravity. And this is just the momentum constraint. They are related with the transformations, the invariance, the symmetries that general relativity has. So this is perhaps also the beauty. This is just a small, I don't know how long I will, but when I'm 20, 15 minutes, just waves, so in order to work about the symmetries of your space-time and in general relativity, and the Hamiltonian is important, as you know, in all other theories. So this allows, for instance, to work out what can be happening near singularities, namely the famous BKL singularity or not. So this is just minor comments that I hope, as I mentioned earlier, that cement how this work by ADM is like unveiling, it's like a scripture. If you are a believer or not, I'm not, like God left something and they unveil it. Oh, okay, that's it. So it is really, okay, now I will go perhaps over this. I'm looking at the clock and I see time has no mercy for me. But this is something that another master produced, and this is something that I can talk perhaps later, is by Claudio Teitelbaum. He set a set of works that are brilliant, like those Flemish, those Dutch master that paint things so perfect. So in the end, he worked out gravity as a gauge theory, but in the sense of defining their secondary and plus the primary constraints that Misnerton and Wheeler and also the had in the sense of first or second class constraints. These are just names that you need to at least to be aware of them. And the point is that when you consider some transformations, and I'm just going very briefly over it, and you insert that there is some configuration variable, then there is a canonical that satisfies this, so you have to have this, then you have general relativity. I'm just mentioning this because this brilliant work by Claudio Teitelbaum has not been perhaps embraced as it should be, in the sense that when you have other gravity theories other than general relativity, this framework that Claudia Teitelbaum has done, at least has not been applied and to prove that they work as they should. So the Poisson brackets, the Hamiltonian, the list of classical first, primary, and secondary constraints, the first and second. So I think this is important when you go towards modified gravity, at least. So at least Claudio Teitelbaum did for this, and more brilliantly, he did this with his students towards supergravity with torsion. So this is neatly done. So this is a remarkable piece of work. So I'm just mentioning this because, as I said, I was asked to be pedagogic. I'm still trying to be. And so now, being a little bit quantum, and I need water. I will drink a lot of water. Don't be upset. So now you have this, the secondary constraints, and you can see this is something that from even perhaps in the Ryan and Shapley book, it's clearly presented. You can see general relativity as a theory, as something where pre-geometry evolves. It's a word that needs to be here taken with a pinch of salt, because time is not explicitly present. And it is because the DeWitt metric has a minus in the signature. It can be shown to be there. So GR is the evolution, in the sense of a Hamiltonian case, of three geometry in this time-like, again, with a pinch of salt. And this is what has been shown by the ADM, Bryce DeWitt, Wheeler, and then also by Teitelbaum. The important issue, and I'm really here being extremely unfair. I'm putting perhaps in a couple of slides work of decades. So this merits actually classes and doing the calculation. They are already presented, but I'm being unfair to the effort that these people have done. And this is just a point of a starting point where many results can be obtained, and also other deviations and routes to be explored. So the point now is that you can quantize things identifying the canonical momentum as we learned about, and then we can substitute in what we have known as secondary constraints and get what is known as the Wheeler-DeWitt equation. It sounds something like that. Now, a bit of a parenthesis, a small break. So, yes, I'm sure that Francesca will show when you use other variables, the Aztec-Carol variables, you have another framework which is also interesting. I'm not focusing on that here, because of course she will be doing that. But the other point that I would like to call here is that you're already seeing here that things can be a little bit tricky now to solve. You are getting a sort of like a Klein-Gordon equation. So this is strictly not helpful, and it will not be helpful. It will be the source of major problems. However, and this is the point I would like to make, is all those old masters, like Hans Bethe in the 1950s, is remarkable. He looked at this and he said, okay, I'm not going a Klein-Gordon thing, I'm going to try to find a Dirac thing. This is 1950s, okay? No supersymmetry, no. So he then worked, this is on the book by Ryan and Shepard, also in Ryan's Hamiltonian Cosmology. They get to something where the wave function of the universe is something that he called question marks, with those marks, double, a spinner, and they stumble on Pauli matrices. This is 1950s, late 1950s. So he doesn't know what it is. It stays there until something that I will mention in a couple of slides is there. So this is already saying something, that we are facing something that is well beyond the mere Cauchy problem or the Hamiltonian stuff. So now we have something that we call the Wheeler-DeWitt equation, which is a second order Klein-Gordon thing, which it is at each point of superspace. Superspace is the space of all three metrics, which are related through spatial diffeomorphism. It's like you have configuration space where some elements can be related with another, and you took a quotient space. So it is a bit like this. The problem again is that hyperbolic operator that is there, and it is already putting a question, a very important question mark actually. Can we use a probabilistic interpretation worse than the problem that we all know by relativistic quantum mechanics of the Klein-Gordon? You will see that this issue of probability is even more serious for a reason that I will come again and I will point again to you. So this means we need something, hence the title of my talk, which seems that I'm ditching things. We need boundary conditions. We need hypotheses. We need to make a choice. So there is something called the no boundary, which is well known. It was proposed by Jim Hartle and Stephen Hawking. Namely, Stephen Hawking and Hartle, all the students work on it. Then there is the tunneling or the Vilenkin. Okay, I'm being metric wise. Okay, I'm not doing anything beyond that. But, and I like to say this. So the no boundary means path integral, basically. Vilenkin means a little bit of WKV, and you try to solve your Wheeler-DeWitt equation, making judicious choices on what you do regarding the from what you start regarding the potential. You can do it straight from the Wheeler-DeWitt equation with a view on something that we call mini superspace, which is another leap of faith. It's an enormous leap of faith. And then there is this recent work by Liners where they do not take the Euclidean path integral, but they took the Lorentzian path integral. So they found out a theory, a mathematical theory called the Picard-Lefschetz theory, where they can work on the Lorentzian, calculate, and use the saddle points and produce results that might be or not useful. So another small point for people that are interested about this of quantum cosmology, which is not a dead subject, in say 2018, 2019, you could see on the internet, on the archive, you could see a paper by, say, Neil Turok or Liners or others, and then suddenly, a couple of weeks later, there was a paper by Halliwell and Herzog saying, okay, but then a couple of weeks later, there comes Liners again. No, there is. So it was really like a tennis match or a chess. It was brilliant. So it was really, if you know what they were doing, that. So in the end of the day, they have not settled that. But there is a point that I hope to have time to mention afterwards, where there is a relation to some thing called Morse theory, n equals to supersymmetry, and some results by Witten that bring this in light or insight of those boundary conditions. So it is still open up. So many things that were done and then shoveled or put on your shelf, maybe they are resurfacing again. So again, now no boundary and more water. This was a proposal in 1983, and actually before in 1982 by Stephen Hawking in his Vatican presentation. But in 1983 is the serious paper in Physical Review, where they come up with the idea, okay, let's do quantum cosmology, let's use the Feynman path integral, and we want to compute the probability of the universe grow from, say, one hypersurfaces to another hypersurfaces. And we calculate adding over all some manifolds during this. This will be already, say, please. I don't. I don't care. Let me proceed. This is just something that when you go to the semi-classical and the saddle points, it's easy to compute. The point here is, even if you go to a Friedman model case, mini superspace, you don't have that. You just calculate the wave function as say e to the minus I, which is the Euclidean action. You calculate the saddle point, and that's it. Most quantum cosmology, it must be honestly said, is just semi-classical. At least quantum cosmology doing Arthur Hawking or Vilenki. By this only to the classical limit. I don't care for two reasons. First, because I didn't consider that in my slides, so that's the easiest way to say it. And it is not important just for the problems that the semi-classical usual treatment brings. Even for Friedman, for homogeneous and isotropic, there is a lot of lurking problem. If I may continue, the problem here is you immediately say, okay, no problem. You Euclideanize, you do a weak rotation, you substitute Lorentzian time by Euclidean time, and then you go from a Klein-Gordon, say an hyperbolic to an elliptic equation, and this will be finite, and that everything is okay. This is perhaps okay in usual field theory, is not okay in gravity. The main problem is that it is unbounded from below. This only works, a brilliant work by Gary Gibbons and Stephen Hawking regarding black holes. They can show that quantum gravity with the Euclidean path integral works well for black holes, but for the universe and the Sitter space, it does not. So if you read the paper then subsequent by Halliwell and Hartle, they found out that you need to have complex metrics. Moreover than that, the lapse function can be negative. Then you have to impose, there is a set of 5 conditions that Halliwell put really neat in that paper, in those set of papers. You really have to impose that in the end, you have to have quantum field tuning curve space that you have the bunch of Davis Vico and so on and so on and so on. So this has to do with one aspect, is that the Hartle-Hawking boundary condition, when you calculate the saddle point, let me just proceed just to, I'm watching my time, and when you calculate the saddle points and so on, you don't have a unique contour. More saddle points, more solutions, and you put them on your calculations, and how now do I proceed? And you have all possibilities, and all possibilities, the degeneracy of the no boundary is there, and you have no answer, you have no guideline how to proceed. All of them, more or so, in a way, they allow to, again, predict. I'm taking this with a pinch of salt, inflation, but again, there is a degeneracy that you cannot lift. You have to live with it, or you need to find something else. This is where linears came in. So this Picard-Lefschetz is something, and I'm trying to use the best of my time. You have something called Lefschetz symbols or symbols. I don't know how to say this in English. I apologize. And there is a function, a Morse function, and how this goes downward or upward, so up or down. You select those that maximize the value of the saddle points on your classical action, and then you can get a way out of this mess of so many contours that you can select. But again, you are not getting in an easy way to what Hartle and Hawking are doing. So now, then you need to put some called Robin boundary conditions, which remarkably, it's saying that the wave function of the universe must be 0, or even the derivative 0, which is called the Robin boundary conditions at the singularity, which again goes back to the Witt in 1967. So there is this degeneracy which is still there, although it must be said, either the no boundary and the Villain can open up the field, and there are important results in homogeneous and isotropic assumptions. So if you go anisotropic and beyond homogeneous, okay, you need a lot of faith that you are doing things. So the point here that I would like to just to say is that what Hartle and Hawking suggests is that the manifolds we are taking are those that are compact and without boundaries, so meaning closed. So this meaning that unless you take the calculation of your wave function on a hypersurface, the universe has no boundary whatsoever. It's like picking up the de Sitter model, that hyperboloid, and you transform it in a force sphere. So in a sphere, you have no boundary, so you have no singularities. So this is, in short, what has been done. But point of order. Again, this is actually remarkable. In the 1950s, 1930s, Einstein wrote an essay where already the Big Bang evolution of the universe was there. So he wrote an essay where he says, okay, the whole universe requires it to be compact, closed, and of finite size. The reasons are not topological, and he was not calculating any path integral or whatsoever. It was more, say, you cannot have the universe with a spatial boundary. It is meaningless. Okay, this puts already some Bianchi models aside, but for him, it's so he didn't want any boundaries. So it is more on the ontological aspect, but then there is this quotation, which when you read the correspondence by these old masters, Einstein, Pauli, and Pauli in his caustic way said, God made the bulk, the surface was invented by the devil. So it is terrible. These people were terrible, but they were there to. Okay, now continue. And well, I have time, please tell me when I have 15 minutes. And I still have water. So now the Vilenkin, I already put there. I changed my slides, and I must say I'm not LaTeX savvy. So whenever I do this, things don't turn out as they should. But the tunneling, the Vilenkin proposal was cast with the mini superspace inside. Mini superspace meaning that you only take homogeneous metrics, and preferably homogeneous and isotropic, because it's much easier to calculate and compute. So Vilenkin, when it goes to something that is homogeneous and isotropic, like the Friedman, with one scale factor and one scalar field, you can cast this as a two-dimensional mini superspace. It is a Minkowski geometry-like, and then, okay, home. And then I can put this as a conformal transformation and put it like this. So only one point of this is just something that you do some coordinate transformations, and only one point here has no infinites. So that's that point. All the others have infinite. So what Vilenkin says is that I want my superspace, but he did this with the view of mini superspace to do calculations. You have singular and non-singular boundaries, but you must have your wave function bounded, otherwise it's ridiculous. And the universe can only enter at singular boundaries, and it can come out only out of singular boundaries and only enters non-singular boundaries, non-singular points over there. So maybe this will help in the next, still looking at the clock there, between the differences between two proposals. So again, I emphasize this. They are proposals. They might work or might not work. They have differences. And you have a lot yet to explore in many issues, still to do. So the point is, you have here the potential for A, and you can consider in outgoing in the, say, the oscillatory region, the Lorentzian, and here the decaying and increasing. So the Hartle-Hawking considers only one type of Euclidean wave function. You can have both outgoing and ingoing. Vilenkin is actually the opposite. So this might sound that this does not matter. Yes, it does. So let me proceed if I can. So we are going now mini superspace. So mini superspace means we only have homogeneous cosmologies, and there is already here an enormous leap of faith. there were works by Bylock Hu and other people where they try to appraise if this truncation is realistic or not. So the jury is still out, okay? So in some cases it may work, but in more general cases it may not work. So is mini superspace truncation valid or not? I don't know, really. It works. It provides something interesting, but if you go beyond, it may not. So the point is that it really provides you with aspect, but then you also have an aspect that I have not mentioned before, but it's written there is the factory ordering. You don't know what to do when you have that second order derivative, and then you have now how your momentum for the scale factor is defined. But you can have something which is, okay, let me have everything conformally invariant, which I can do for the 2-dimension. At least I have something which can sort of guide me. But beyond that, you don't know. So one aspect, and I'm trying perhaps to shuffle quickly, you can go WKB. Again, going WKB will put you, if I can reach a couple of slides, if not, it will go for the other, in a huge challenge. So let me just say that that was a talk I attended. It was 1997. And the speaker, I think, was Neil Cornish, which was at the time a postdoc with Paul Shellard. Or was Paul Shellard, and Stephen Hawking was in the audience. And you could notice how the aspect of WKB not being so neat for the Hartle-Hawking or not. So this is something that it works. You can do calculations with this, like in common quantum mechanics, a little bit more worked out, as you can see. But in the end, you have oscillatory functions, say when the scale factor has large values, and you have here, say, just the exponential type. So you can have classical and quantum or oscillatory or Euclidean. So you can solve this for this simple case, Then let me just flash you very quickly. So you can see that the saddle point approximation for the Hartle-Hawking is really a sum of the incoming and outgoing in the classical region that can be written in this way. And then when you go to the Vilenkian, and you can see that it's actually different. So it is actually not the same. So one is real, well, and the other is not. So does this make any difference? Yes, it does. And this has been the source, say, in the late 80s, and we are Don Page and many 15 minutes. Thank you so much. You are presenting this for a while, and I was ignoring you. So my apology, my sincere apology. So the point is that you are assuming homogeneous and isotropy. Otherwise, you cannot do clean calculation. And then you are assuming either one or the other. And then you take the word predict here with a huge pinch of salt. So either of them predict in the sense that the wave function can be strongly picked for this solution. So again, you cannot use here quantum mechanics as we know with, say, normalizable to one. So they are not normalized. But you can define near the trajectories on mini superspace probability density, and you can see here the differences between the Vilenkian and the Hartle-Hawking. So one is far better for lower values of phi. And again, another point of order, they are taking here phi square. So these were the times where the chaotic model of the phi square potential for cosmology was the only one. Now we know that is in big trouble regarding the data from Planck. So they were assuming that they were already seeing that, okay, the probability maybe favors here larger values of phi if v phi is phi square is smaller values. So this can be a problem if you go beyond the Planck scale or not. Actually, the whole argument turns around when you have conditional probability. So in the end, it's really model dependent, but there is a big if. So in the end, it's something that you depend on what you assume, on what you take. So this is still a problem. And it's worse a problem if you try to, okay, maybe I don't want things to be isotropic. Let me try to be anisotropic. God help you, or God help, or anyone help you. I don't mean that. It just, I'm not a believer. I'm just using. Okay, now I'm going to this really fast because I wanted to point to something that I can come up with at other occasions. This is something that has been the bulk work of Halliwell, Raymond Laflamme as well, but surely also Klaus Kiefer. And they are, okay, let me go beyond the simple cases and let me try to deciphering what are God whispers. The question is, what do you do when you have fluctuations, perturbations, and you need to have decoherence, and you have many WQV branches, and you have quantum interferences? So this is something that can work in some simple cases with decoherence functional, but again, it's just for those simple cases. So in the end, you cannot ignore the fact that you have the possibility of interference, and you have something that is the environment, the fluctuation that might help you. Or not. Sorry, I apologize. One click too many. If you take WKB approximations, they might actually interfere at a turning point. So classical time might not be possible. Tragedy. Then you may have something that you don't want, that is back reaction of non-gravitational fields on the Hamilton-Jacobi equation, double tragedy. So this is something that you need to stop somewhere. I don't have time to go through all of this. I can point where these are. So this is basically the brilliant work by Klaus Kiefer. I would like to make this clear, where you really need to take with care what happens when you go beyond the semi-classical and the WKB. So what we can call quantum gravitational correction to the Schrödinger equation. It's terrible. You have two types of contributions, the tangential and the orthogonal. When you consider the orthogonal ones, you may do some computations, but you are facing the possibility of some terms. I'm really being a bit a little bit technical here and non-presenting there. You get non-unitary terms. Regarding the orthogonal, no one has done it before. So it's there. So there are many things that are open up, and you can still ask if the bunch Davis, yes, it is, you can get it, but okay, now I still have 10 minutes, 10 minutes, 10, 5, 9 minutes. Okay. Let me get more water. You are young people, and my audience is filled with young people. I'm already old and I need water for my medical, but I'm not doing anything indecent, don't worry. Oh gosh. Tell him I will not reply. I don't see what is.
Can I ask you questions? Hi, Paulo.
Yeah, 1 second.
Yeah, I hope you can hear me. Well, you mentioned about the inflationary universe from tunneling.
I don't hear it, but he write it. I will write, and I will write.
Shravan, 1 second. We are fixing the audio.
Okay.
Okay, now yes. You can go.
Hi, Paulo.
Hello.
I hope you can hear me now.
Yeah.
Okay. Well, you mentioned about emergence of inflationary universe from tunneling or no boundary proposal, but in the context of chaotic inflation, but Vilenkin first derived for Stravinsky inflation. He showed that Stravinsky inflation can most likely emerge from tunneling. Am I correct?
Yes, but I will not go to Stravinsky inflation, meaning the R2. I know that the Stravinsky case can be cast in a sense of Einstein-Hilbert with the fancy potential. But that is a transformation of going like from the Jordan frame to the Einstein frame. And when you go quantum mechanical, I remember a paper by Donald Page where he says that classical, everything is nice, but quantum mechanically, the functions are not cleanly related. So besides this comment, I will make no other. So I reach a certain age where I can say some things, but also it prevents me to say other things without reading them first. So I hope you accept my comment as such. And I would like to proceed because I only have now 7 minutes. 7 minutes, okay, I have 7 minutes. So there are several issues that are still there. So the issue of supersymmetry is lurking since the 1950s with those works by Bethe and then by Ryan and Shapley, and you are looking at them and supersymmetry has not yet been created, and they are having something that looks like a spinner, but it's not a spinner. And then you have something there which is actually Pauli matrices, but they are not actually using them as what now we know as the supersymmetry generation. The aspect is that they have n equals 2, and this is something that also appears in the Picard-Lefschetz. So the terms that contribute to maximize the Morse function in the Picard-Lefschetz procedure are ground states of n equals 2 supersymmetry, Edward, Witt, and Dixit. So anyway, this doesn't help much because if you pick up n equals 1 supergravity and you pick up just Friedman models, again, a lot of assumptions, a lot of simplifications, I'm imposing things, you get n equals 4. So you don't know how to get n equals 2, but it's still there. The point is, let me just come to this, is you have a sort of a Dirac-wise presentation of your constraints in algebra, which involves second-class constraints, which is something that goes back to Dirac as well. And now you must solve these equations. And in the end of the day, you do solve them. They are linear, they are linear in the momentum, like in a Dirac equation. This allows to simplify things and you get some solution. So this sounds, wow, you made it. No, I didn't. If I go beyond the Friedman case, no one knows it's a huge mess. So it's not good. So only in a specific case you get the Hartle-Hog. So now something that I've been also, I'm just now mentioning 5 minutes.
Yes.
Okay. So I've been curious about this. Don't ask me how did I come across this. It was the last time I was doing a sabbatical and I was at that round library. And I don't know how I stumbled on a work and I found it funny. So let's try to use fractional calculus in cosmology or quantum cosmology. The idea is that instead of having two second derivative, third derivative, why not have rational, real, or even complex? So this sounds silly. I'm not using any word, but actually people take this very seriously. So in applied math and physics, in all this, now in solid state physics, because the mass of the electron or the what we call the hole, I don't know if it is the word in English, can depend on k. K is the wave number, which is related to the momentum. And if you use fractional derivatives, it can be actually very useful in the Ising model. I don't know how, but that's what they say. So it is not something that comes out. Well, let's do this. So in the end of the day, you can use space fractional derivatives defined like this, with alpha goes from 1 to 2. Now I'm using alpha as a measure of the dimension of the fractal dimension, and you can also have time fractional derivatives. So all these things are rigorously mathematically defined. In the end of the day, they allow you, for example, to have if I can be very crude about it. You have one, and you put an additional parameter on your equation, and you can play with this additional parameter with all the other parameters. So it's just this. So you just do. So the point is, when you go doing some computation of entropy, namely in black holes, and you have either the solids and the Beira holographic, you can cast them on a fractional. So now, very quickly, another thing that talk by Neil Cornish and Paul Shellert in 1997, and to my knowledge, to my humble knowledge, no one else after that has picked up. This is very complicated, so it's not to my brain. So, but the idea here is the following: is when you have chaos, which is this exponentially propagating errors, you are doing this classical. If you have quantum mechanics and this is linear, you don't know how to bring up chaos from the quantum. So then Einstein. So this is remarkable again. In 1917, he wrote a paper which is mathematically about topology. So he put the question: how can quantum mechanical be formulated for ergodicity? So this has not been integral solutions, because for them you have the Bohr-Sommerfeld quantization. So those mean that your trajectories are like closed trajectories, like orbits that close up sections submanifolds of a tori. So how one does this? This is the open question that remains to be addressed since ever. This was forgotten, this paper, for 40 years. Then a guy called Keller in Germany in 1957, he picked up the results, and then he goes to the Einstein-Brillouin-Kramers quantization. And then quite a few other people try to think about this. Billiards are not just balls that are going to mechanical walls, and if you change them, you get trajectories that are not easy reflection, but they are now bringing chaos. And then you think, okay, now let's do this with waves, which we call quantum billiard. Is now this eigenvalue problem. You get that equation, and we go, let me just put everything here, to that question made by Mark Katz in 1966. The answer to that question is actually no. You cannot hear the shape of a drum. But the point is, maybe in working this out, the spectroscopy, you can learn something about the shape of the universe and what are the variables that it's already over my time. So I'll go very quick. So this is the talk by Shellert and Cornish. And the point here is very quickly, and the conjecture by Don Page, is that when you go to WKB, you are ignoring that other trajectories are chaotic. No one has done anything regarding the Vilenkin approach, because the work by Cornish and Shellert was strictly on the no boundary. So this is, someone can do it. So this sounds a silly title for a set of slides, but it's nothing to, it's just to say that you can try to go beyond the boundary thing, and using the conjecture by DeWitt back in 1967, he says constraints are everything, and you should not need anything else. Don't make any boundary condition, just use the constraint. So there are results that can be said about this. I'll go through this perhaps. Sorry, this is my slide before the last. So these are questions. I'm not very good in many open questions, like, okay, what's the nature of dark matter? I don't know. Where do you put your money for dark matter? I'll put primordial black holes. I don't remember now that former student by Stephen Hawking, he's a deep friend of mine. He's in Queen Mary College, or was in Bradencar. So I like him very much. I hope primordial black holes are found. He will be very happy. So the point is that you still have, can this be possible? So in the end, what happens if you put some additional structure in your space-time? And I will leave this perhaps to the, and I will just end like this. So if you want to read better and learn more, you have this amazing corpus by Klaus Kiefer. So this is for me the best of the best, and you don't need anything else. He's preparing, let's hope he can make it, a new edition this year. Then you have this less well-known, but brilliantly written by David Wiltshire. Then there are other papers here. This is the one by Liners. If you want to see about questions, you can see here. And if you are curious about quantum cosmology and you don't want to take it too much, you have this anti-branding. So this is before you take a meal. This is a slide share show. And thank you so much. Sorry about
Thanks,
the time
Paulo.
I took it here.
So we are running out of time. So we have time for one understanding question.
One understanding question. Yes.
Something I don't understand. So I would like to go back to my question. So you said that one of the reasons why you compare it is because you take the classical limit, but even in that limit, I'm confused that you can neglect the definition of the measure, because imagine that the measure is somehow defined as a function of the metric times the usual definition of measure, which is the product of the ratio of the metric at each time point. Then this function can be created basically a redefinition of the action, and then depending on definition of your measure, you will get different classical limits, because the action will just be shifted by an arbitrary function of the metric. So I don't understand how to get predictions without knowing the definition of the measure.
Okay, let me very quickly say the following is, if you are doing full quantum gravity, of course, that's important. But most quantum cosmology is like a pragmatical, let's try to get something out of it to see if it makes any sense of it. If for the simple cases you get no sense, forget it. So this is just, let's just do some back of the envelope calculation. So if you now take semi-classical, so WKB, and you want to calculate this wave, the Hartle-Hawking wave function, of course, you can take just common dA, d phi, dn for the lapse, and then this is just a common integral, and you just substitute there, and this is plain measures like in calculus 1. So that's what you do, pragmatic. I agree that if you want to be more serious, if you want to go super space, you will need to do that.
By the end,
It's like
it seems to be not defined as long as you don't define those measures.
it that let's imagine
The action, you don't define
let's imagine
the minus delta I times some.
it is not. It's just common calculus dx, dy, dA. So this is just common integral. That's how you do the Hartle-Hawking in a very simple case. It's trying to get from here what you will get from the WKB. I agree that it might be not to the everybody's pleasure, but that's how it is done. You can go to that paper.
You didn't define how it is done.
You don't define it. As I said, I don't care about it. I just do it.
To get those results there, psi HH approximately equal to this curly bracket, and then you have to define the measure.
You just put dA, common differential dA.
Oh, okay. So this was my question. So you just put
Exactly.
dA.
It is
Okay.
triggered than that, but that's a good
I'm
point to discuss
it
in
just-
the
You define the measure as just the normal
Yeah.
product over.
just integral.
This is already so much mess, and for a simple problem and the problems that come afterwards, that I agree that if you want to,
Don't understand.
I need more water. I don't know which is my glass. No, fine.
Okay, I think this is a good point to close the discussion and
Grazie.
proceed with the coffee break. So thanks, Paolo, again.
Thank you.